Find the divergence of the vector field. Our vector field F, 3 entries, x, y, z, secant x, y, z, arctangent x, y, z squared. Z squared. Okay, all right. Now, what do we mean by divergence? It's actually the good kind, because there's more or less 3, we'll call them derivatives going on here when we talk about vector fields are related to vector fields. And divergence, that's the one which we can also denote with the dot product. It's del dot f. And here we have 3 variables, so this is writing it out: partial x, partial y, partial z, dot e to the x, y, z, secant x, y, z, and arctangent x, y, z squared. And we do what you think you should do with the dot product, right? Term by term. So now I'm doing this very slowly because otherwise we'd be done in like 60 seconds. And probably like, isn't that a good thing? Well, it's good to do it out the long way, at least once. So it says take the derivative with respect to x of the first entry, add the derivative with respect to y of the second entry, and then add the derivative with respect to z of the last entry. And one thing we should note is at the end of this process, we're not going to have a vector. We're going to have a function. So when you're doing divergence, if you end up with a vector, you didn't do the divergence. I don't know what you did, but it wasn't divergence. So make sure, it's not a vector where you take derivative of the first thought, take derivative of the second. No. It's a function at the end. So make sure, function. Okay. All right, well now, just take derivatives. We're taking derivative with respect to x, y, and z are acting like constants. So here it's like e to the x times a constant. So it's, that constant, yz, e to the x, y, z. Derivative of secant is secant tangent. All right, and so secant tangent, plug the inside in, and then here, derivative with respect to y, x and z are my constants, so xz is the constant, goes down in front. Now arctangent, arctangent, good function. All right, so it's derivative of arctangent 1 over 1 plus xyz squared, right? Then times the derivative of xyz squared with respect to z. Well, that would be a 2xyz. And we're done. That's it. Ta-da! Wow, that's nice. What a lovely problem. So remember, divergence, dot product. If it helps, D for dot, right? Divergence is dot. We're going to talk about curl in a second. Curl, C, cross. All right, so dot product, get a function out. Make sure you don't end up with a vector, but otherwise, no surprises. And this one's the funnest one of all. And of course, you might think, is there anything you can do with divergence? Oh yeah, that's coming up. Find the curl of the vector field F is x squared y plus 3xzi plus e to the y plus z minus 3x squared z j plus xy cubed minus 17z k. All right, so curl, again, it's kind of like a derivative, but it's a very special derivative. And it's something that you have to start with the 3-dimensional vector. Doesn't work for 2D vectors, doesn't work for 4D vectors. Has to be 3D. And you're going to end up with a 3D vector. And so, where does the curl come from? Well, curl, cross, right? They both start with C, curl, cross. So, curl of F is del cross F. Okay, good. Now, del, that's your collection of partial derivatives. partial x, partial y, partial z. Cross, and well, here I'll put this into component form. So you have your x squared y plus 3x z, comma, e to the y plus z minus 3x squared z, comma, x y cubed minus 17z. All right, there we go. Now, we're going to take our curl, that's the cross product, so we're going to set up our matrix. You can memorize formulas, but they tend to be hard to remember sometimes, especially because there's so much alphabet soup going on. So curl is one where I highly recommend learn the process. So if you learn the process, no problems. And all right, so what's the process here? We're going to set up our determinant. It's going to be a very weird determinant if you think about it. So in some sense, I'm not saying don't think about it, but just sort of say, look, just go with it. And so you have in the first row, I, j, k, those are your vectors. Second row comes from your nabla, your del, partial x, partial y, partial z. And the third are these individual pieces, x squared y plus 3xz, e to the y plus z minus 3x squared z, and xy cubed minus 17z. All right. Well, now we begin. And we have our diagonals. So we're going to do our down diagonals. So I'm just going to emphasize you have these diagonals going in that direction. And now what happens on those? Well, we're going to take partial y of xy cubed minus 17z. And that's in the I direction. So because we're taking derivative with respect to y, z and x are constants. So we're going to end up with a 3xy squared. Okay. Now, j, partial z of x squared y plus 3xz. Well, there's only one z here, and everything else is a constant, so we can get plus 3x in the j direction. All right, k, partial x of e to the y plus z minus 3x squared z. Okay, again, derivative with respect to x, y and z are constants, so this becomes plus minus 6xz, and that's in the k direction. All right, now, those are half of it, right? We have to do the other half. Okay, so there's the going uphill in some sense. All right, so let's read what those are. We want to take the derivative with respect to y of x squared y plus 3xz. Well, when we take that derivative, what do we have? Y is the thing that's varying. Everything else is constant, so it's x squared. And we're going to subtract because we're going in the uphill direction. Okay, so next term, we're going to have the I direction. Take the derivative with respect to z of e to the y plus z minus 3x squared z. So y and x are constants. So we say, okay, so what do we have? Well, we have a 1 minus 3x squared. All right, and so that's 1 minus 3x squared. That's in the I direction, and we're subtracting. Our last one. So that's our j direction, derivative with respect to x of xy cubed minus 17z. And what happens? Take derivative with respect to x, y cubed is what's left, and that's in the j direction, and we subtract. All right, good. Now we just have to put this all together, and we'll be done. And we have to make a choice. How to represent the vector, and let's use the notation they provided. They like that notation, so why not? Let's go with it. So we'll put things together. We have In the I, we have a 3xy squared minus 1 plus 3x squared plus our j, 3x minus y cubed j. And then plus minus 6xz minus x squared k. And we're done. And notice, we started with a three-dimensional vector. We ended with the three-dimensional vector. That's what you need to do when you get the curl. Now, it could be that some of the entries are 0. That's all right. But still, it needs to be a three-dimensional vector. Not a function, not a number, a vector. And great. And you might say, well, can you do anything with curl? Yes! Yes! We're not just learning things for the sake of like, oh, here's this computation we can do. There's beautiful things. Essentially, it's a derivative. And we're going to see some beautiful applications of it. And that's coming up, not during this session, but in the next several lectures of the class. So I hope you keep coming. Now, you might ask a question, and since we seem to have a lot of time, let's go ahead and ask the following. There's some pieces that didn't seem to make any contribution. Notice nothing looks like e to the y, and there's nothing with a 17. Why did those pieces not show up? Can you see why? So think about what's happening here. When we're taking our, determinant, we're going at angles. So when I'm looking at this term here, it will only have a derivative with respect to x and only a derivative with respect to z. So I'll never get a derivative with respect to y. Since that only depends on y, it will always vanish. In a similar way, here, see how it's right below the derivative with respect to z? So I'm only going to either take the derivative with respect to y or with respect to x. So anything that depends only on z will vanish. What that means is you can start with a very complicated f, but by taking the curl, the complicated parts can disappear. And that's one of the things that often test writers and problem writers like to do. They're like, ooh, look how complicated this is. And then you're like, okay, well, let me do this step. Like, whoa, it's not so complicated. And it's like, ha, 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 you fell for our trap. No, that's not what they say. They say, exactly like we intended. And so yeah, even if things look bad, don't panic, right? Just trust the process and follow the procedure. And, it's like the saying goes. It often, it's the most dark just before it goes pitch black, right? No. There's always hope. Always hope. Know your rules. Know your procedures. Find the mass, m, of a thin wire that lies along the curve. R of t is 7, 9 minus 6t, 8t. Time goes from 0 to 2 pi. If its density is given by delta equals 3, 4 plus sine 6t. All right. Now, what a fun problem. What are we doing here? Well, it's mass of a wire. I will say, for mass of a wire, it's kind of a very bland problem, but you'll see that things are like, this is not that exciting. On the other hand, you're probably like, yay, this is a very bland problem. So I'm going to point a couple things out as we go through here. One of the first things I want to point out is it's a little bit unusual the way this problem has been stated, namely the way that density is given. They've written it as a function of t. Normally, when we have problems like this, they'll write density in terms of x, y, and z, and then we have to convert it into t. That's okay. We'll just go with it as it's written. No worries. But keep in mind, sometimes you'll have to do a conversion. Say, this is given to us as a function of t, but it may not have been given in general. So be open to it. The other thing that makes it kind of not super exciting is when you look at this wire, it's basically a straight line. Oh, it'd be interesting if we could bend the wire. But of course, as soon as you start bending the wire, the integrals involved start getting more interesting, also known as not enjoyable. So that's probably why they did that. Okay, so we want mass. Whenever you see a problem that says find mass, it's always the same procedure. So there's no surprise here. We say, well, if we want mass, we integrate our density. And that's the formula. Now, this part doesn't change. What might change is what kind of integral you do. So, why did we write this type of integral? Well, we're in a one-dimensional object. So, we should have one integral sign. Also, it's an integral along a curve. So we use the notation to say, oh, integral along a curve. And what's the idea? Well, we have a curve, and we're just breaking up into little tiny pieces. And the little tiny pieces, we say, what's the mass of, say, this piece right there? Well, what you do is you take the density at that section times the length of that section, and that's the mass of that piece, and then integration says add it up. So let's remind ourselves a couple of things. Let's go through the process so we're ready for anything more interesting that might come along. What is the ds? How do you find it? So ds, that's this part, it's basically a little segment of length. Now we're in a three-dimensional setting, in theory, and so we say, okay, channel the time when we talked about arc length for 3D. And you might remember there was the formula where you had your x prime squared plus y prime squared plus z prime squared dt. And that's your ds. All right, and then say, okay, well, what's your density? Well, it's what they gave us as. We don't have to convert it to t. They already did the conversion for us. So it's 3 times 4 plus sine 6t. And then, of course, the integral, we now update because we put it all in terms of t. So the bounds go 0 to 2 pi. And, well, that's what's going to happen. We do need to clean these terms up. Well, let's figure these things out. What is x prime of t? 0. Nice. Y prime, negative 6. And then we're going to square that. Z prime, 8. And then we're going to square that. And now, if you look, you say, well, that's 0 plus 36 plus 64. Well, that makes 100. Now, that's nice, because there's no t inside the integral. And not only is it nice, because there's no t, it's a nice number. Square root of 100 is 10. So you can like pull that out and like, woohoo, nice. Okay, so we're going to do that. We pull it all the way out. We pull out the 3 too. So we really have 30 integral 0 to 2 pi of 4 plus sine of 6t. All right, so there we go. We write everything in terms of t, using the ds becomes, piece of arc length, and then clean it up. And now, Calc 1 stuff, right? And indeed, a lot of what we do feels like Calc 1 stuff. No coincidence. And, all right, so what do we have? 30. And then we're going to get 4t plus the integral of sine is 1/6 and times a minus cosine 6t. The minus because the integral of sine is negative, cosine the 6 because you have to compensate for the 6 on the inside. And we're evaluating from 0 to 2 pi. Well, okay, so what do you have? You have 30 times 8 pi, and then cosine of 2 pi is 1. So minus the 6, and then we're going to subtract, and 4 times 0 is 0, cosine of 0 is 1, so we're going to subtract now minus the 6, and you'll see that these actually end up canceling, So our final answer is 240 pi. And that's it. We're done. We did it. Woohoo! Nice. All right. No big surprises. The procedures, all right. If anything, I hate to call problems a little bit too simple. This one was a little bit more watered down. Make sure you understand the procedure, knowing how to do DS, knowing how to write density. And then, even if the problem isn't so straightforward, you'll be fine. You can do this. You're great. Come on, do it. Do it. Find values of B and C so that we have this vector field, or vector valued function, and we want it to be a gradient field. Okay, so let's remind ourselves, what does it mean to be a gradient field? So a gradient field, or if you like just a gradient vector valued function, means that this capital F looks like the gradient of some little f. So there's a potential function out there. Now, it's not asking us to find the potential function. We could figure out, well, what potential function would make it work, and what would it force on the values of your B and C. But instead of saying, hey, we have to find values of B and C so that it is a gradient field. So we should say, okay, do we have a test? Is there some way for us to test if something is a gradient field? And there is. Okay, so here's the test. What you do is, if it's a three-dimensional vector, you do the following. Your gradient field, and sorry, this is a dramatic pause here. You're like, whoa, what's he going to say? If and only if, so that's what these arrows mean, you have that the curl is equal to 0. So essentially there's a collection of partial derivatives which have to match. It all boils down to the curl being 0. So what do? Well, let's take the curl, set it equal to 0, and say, what does this say about B and C? It's possible that we'll get exact values for B and C. It's possible that any B and C might work. It's also possible that no B and C might work, and it'll never be a gradient field, in which case we got to go back and rewrite the problem. So let's just do the computation. So another chance for us to practice curling. That's right. It's not just for Canadians. We can all curl, right? Right. Okay, so we're going to do our I, J, K. Give ourselves lots of space because functions take a lot to write down. We have our partial derivatives, partial x, partial y, partial z, and we start copying down. Y cubed plus 4cxz cubed. I'll distribute through bxy squared plus 3cz squared y squared, and then our last one, 2zy cubed plus 6cx squared z squared. Good. All right. And now just work through it, right? And be patient. And here, it's going to be really important for when you take your partial derivatives, right? So we're going to have our 3 diagonals going down, and we'll follow that by 3 diagonals going up. But going down, we have, in the I direction, take the derivative with respect to y of 2zy cubed plus 6cx squared z squared. Now that will go away. The only place where y shows up is there. So we end up with our 6zy squared. We could really put that as 6y squared z. Why not? Okay, might as well go alphabetical order. All right, good. Now, j, derivative with respect to z of y cubed plus 4cx z cubed. Well, derivative with respect to z, that goes away. Here, z cubed will become 3z squared. Everything else is a constant. So we get 12cxz squared j. All right, k, derivative with respect to x, bxy squared. There's only one x, so that's going to make it pretty easy. So that'll be by squared Okay. All right. Now the other direction, an uphill. Okay, so let's start. Starting here, we're in the k direction, derivative with respect to y cubed plus 4cx cubed. Well, there's only one y, so we're going to get 3y squared. And we're going uphill, so we subtract. All right, next one, derivative with respect to z. This is in the I direction. That has no z. That has z squared. Root of that is 2z. So that'll give us a 6c z y squared. Well, I'll write as y squared z. And, okay, that's in the I direction, and we subtract. And the last one, derivative with respect to x of 2zy cubed, 6cx squared z squared. That's in the j direction. There's only one x, so that makes it simple. So it'll be, 2 comes down, so it'll be 12cx z squared. 12cx z squared. Subtract in the j direction. All right, good, good. Now we start seeing what do we have here. Well, this is equal to, in our first slot, in the I slot, well, both have y squared z, that's good. Both have 6. And what do we really have here? Well, if we factor out what they have in common, we get 6y squared z times 1 minus c. Okay, great. In the second slot, exactly the same. 0. In the third slot, well, there's a y squared. We can pull that out. Y squared b minus 3. Now, remember, what's our goal? We want it to be 0. So we say, okay, we need this to be 0. We need this to be 0. We're like, oh, I know choices. I should choose b to be 3, c to be 1. And there we go. There's a set of choices which will give us what we need. It'll guarantee that we're a gradient field. And in fact, these are the only choices which will give us our gradient field. So, woohoo! Nice! Evaluate the integral along the curve y cosine 4/3 c ds, where c is the portion of the circular helix given by x is cosine 4t, y is sine 4t, z is 3t, and time goes from 0 to pi over 8. All right, cool, 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 cool. So, what do we do? Well, whenever we have a curve, even though it looks like there's multiple variables involved, we know it's a one-dimensional integral. How do we know that? Well, because we can count. We see one integral sign. So it's a 1D integral, which means ultimately when we go to compute this, we're going to get it down to a single variable. And so that variable is t. All right, so we are going to do the following. We're going to say everywhere where we see a y, we put sine of 4t. Everywhere we see a z, we put 3t. And then we say everywhere we see an x, well, we don't. Whew! So we don't have to replace it. Well, there kind of is an x, though, because there's this ds part. So let's do that computation first. So let's do ds. So that's going to be the square root of our x prime squared plus our y prime squared plus our z prime squared dt, which is square root of, take the derivative with respect to x, derivative of cosine 4t is minus 4 sine 4t squared. Derivative of sine 4t is a positive 4 cosine 4t squared, and derivative of 3t is 3 squared. All right, well, if we work on the inside a little bit, that's 16 sine squared of 4t plus 16 cosine squared of 4t, and then we're like 16 sine squared plus 16 cosine squared, they'll combine to give us 16. In the meanwhile, we have this 3 squared, which is 9. 16 plus 9 is 25. So we have really the square root of 25, which is also known as 5. Ah, phew, good. We dodged another bullet because ds can get really complicated, and then it can be a very interesting integral that we have to do. But in this case, we're okay. We're doing great. So we're now ready to rewrite it. All right, so we have the following. Our integral along our curve of y cosine 4/3 z, for all those Britain fans out there, ds is equal to integral 0 to pi over 8. And then we're going to have y becomes sine of 4t. And then cosine 4/3 times z. Well, z is 3t. 4/3 times 3t makes 4t. Oh, well, that's very convenient. Then ds is 5 dt. All right. Nice. Nice. Now, because they were generous, they said, hey, these pieces, they actually match with each other. Now, there's a couple things we could do. We could just say, oh, hey, let's set u equals sine, then du looks like cosine. We could do u equals cosine, du equals sine. We could do double angle. They're all going to work. And they're all about the same amount of work. I don't know. I'm in the mood. Let's do a substitution. Lots of ways to do integrals. Do what works for you. So I'll let u equals sine of 4t. Then du is 4 cosine 4t dt. Or I can move that 4 across because constants are easy to move around. And if we do that, we already have a 5. We're going to introduce a 4th. So that gets us 5/4 integral. The sine of 4t is the u. And then, of course, the cosine dt with the 1/4. Well, the cosine 4t dt gets us our 1/4 du. Now, update the bounds. You should always update the bounds if it's a definite integral. Plug in 0. Sine of 0, 0. Pi 8 times 4. Well, that's like 4 pi 8s, or pi halves. Sine of pi halves, 1. All right. Integral from 0 to 1 of u. Well, that sounds like an integral we could probably succeed at. So that's 5/4 times 1/2 u squared. Evaluate from 0 to 1. And you plug in 0, you get 0. You plug in 1, you get 1. So we end up with 5/8. There we go. We're done. Woohoo! Nice. All right. No big surprises. Just, make sure you know your ds. ds is not dt. And so if you forgot that, you'd have gone in a 1/8. And you're like, wait, what? Where'd the 5 come from? You got to make sure you update. Everything has to be put in terms of t. That includes the ds. But otherwise, yeah, life is good. Nice. Find the work done by the force F of xy equals y squared I plus xj, which means our force is varying depending on our location. And we move along the curve consisting of line segments from the point 1, 1 to 4, 1, and then from 4, 1 to 4, 3. All right, let's sketch where this is. Let's see our journey we're about to take. So we're going to start at 1, 1. And okay, let's mark it. Here we are, 1, 1. And then we move horizontally to 4, 1. And then we move horizontally up to this point, 4, 3. So we're doing a little action. All right, good. Now, how do we find work? Well, the very simplest way we do work, and that's when we're beginning talking about learning work, is it's force times distance. All right. And now that's if your force is always the same, your distance is in a nice straight line, everything's happy. Well, what happens as we get more complicated, especially if we say force is no longer just a single number, but a vector? Well, now we switch from force times distance to force dot displacement. And essentially you're saying how much of the force is actually going into moving this object. So any work is actually like, hey, it actually has to produce something. You can have wasted force. Now we say, okay, great. So, but how do we do it if we have varying force? Integration comes in and says, hey, idea. Let's break it up into lots of little pieces. And then we'll figure out the contribution of each little piece to the work, and we'll add up and get our total. So a little piece to our work looks like the following. If I'm moving along a curve, you take the force dot the displacement. Well, you need a direction of the displacement. That's the tangent vector along the curve, and then a little bit of length. Now add it up, and that gets you your total. So that's your work. Now there's a couple of ways to write this. This is the same as writing F dot dr, or it's the same as writing m dx plus n dy. And this is my favorite notation. Now just as a reminder, what is m and m? That's the entries of F. Now, before we begin and do a lot of work, can we save ourselves some work? Remember, when we do line integrals of this form, there is a nice case. Namely, if what we have is conservative. So it doesn't hurt to check. Is this conservative? Now, there's a couple ways to check. You can try to find what it would be. You can also take partial derivatives. Here, if you take derivative with respect to y, and here, if you take derivative with respect to x and compare, you find out they are not the same. This is not conservative. What does that mean? Well, to quote our good friend the Hospital, more work, more work. So when it's not conservative, you've got to go through and do the computation, because it's going to depend on the journey you take. So here I'm going across and up. It would be different than if I went up then across. And it would be different than if I went on a straight line. These will all give potentially different answers, and they should. And so we have to be careful and go through and check it out. So let's split our journey up. And we'll think of it as two legs. So we have curve 1 and curve 2. Now curve 1, when we look at it, we say, hey, look at this y component. It's always a 1. So that makes it easy. And then the x component varies, so we'll have t. And we're allowed to pick our variation, so that's why I put t here. And I'll say that t goes from 1 up to 4. Now on curve 2, and now it's completely different. So I can forget anything dealing with curve 1. Curve 2 is its own curve. You know, we do it every curve separately. So I'm allowed to reuse t. I'm allowed to have my time intervals overlap. That's all fine. 4 is the xi all the time. And then the y value is varying, so I'll put it as t. And why put it as t? Well, because remember, any parameterization works. We just have to make sure we start and stop at the right place. And there's this implicit, we move from here to here, from here to here. So there is an orientation. Respect the orientation, but also remember, we love ourselves. We want to be good to ourselves. And so we're going to give ourselves the simplest parameterizations that work. All right, so now let's work through these. Okay, well, we'll begin, right? So, integral along curve 1 of m dx plus n dy. So I'm going to write this down. So this is our m, and this is our n. So we have y squared dx, and then plus x dy. And now, remember, what do you do to write these integrals? Well, everywhere you see an x, we replace it with x of t. Everywhere we see a y, put y of t. Everywhere you see an a dx, put x prime of t. Everywhere you see a dy, put y prime of t. So, for us, on curve 1, we see we're going to get y squared. And, oh, by the way, our bounds are 1 to 4. So we're going to get y squared, which is 1. Dx is 1. And then plus x, which is t, times dy, which is 0. All right, so we're integrating 1 to 4 dt. Well, that's t evaluated from 1 to 4, which is 3. Whew, okay, that was not a bad integral. And why? Well, because we're dealing with very simple expressions. We like that. All right, now let's do curve 2. And, okay, so again, y squared dx plus x dy. We're going 1 to 3. And what do we have? Y squared. That's t squared. Dx, 0. X, 4. Dy, 1. All right. Well, that becomes the integral from 1 to 3 of 4 dt. That's 4t, evaluated from 1 to 3. 12 minus 4, that makes 8. And now, put these together, add, and our work is 11. So it's 11 units of work to move from this point up to that point, if we travel in that way. All right, and yeah, woo, oh, good. That wasn't too bad, right? Yeah, just remember the rules and know how to set up work. And then it'll all work out, right? Yeah, of course, because we know what we're doing. We're great. Evaluate the integral along the curve of 2xy cubed plus 5y dx plus 3x squared y squared plus 5x minus 2y dy, where c is any smooth curve from 2, 1 to 3, 4. Now you might say, whoa, wait a second. We're missing information, right? They didn't tell us what the curve was. They just said it's any smooth curve. But actually, this is tremendous amounts of information, because they said, look, it's not going to matter. And if you're hung up on the word smooth, that just means it doesn't get wild and crazy. You could draw it in a nice flowing motion. So it's just a nice curve. Now, that tells us curve independence. The only way we can get curve independence is if we're dealing with a conservative function. So this is a conservative line integral. And as a reminder, what does that tell us? Well, it says that the integral along a curve of a conservative function, so gradient of f of some function little f, dot dr, which is just another way to write this expression, is equal to the potential function evaluated from your start to your end. So in other words, it's f at your end minus f at your start. And they've told us where our start and end are. So we start at, in our case, it's 2, 1, and we end at 3, 4. So it's f of 3, 4, subtract f of 2, 1. End, subtract start. All right, so this problem is mostly about finding the f, find the potential function. And we have ways to do this because we have a lot of information. And in particular, we say the way that this is written is if this is a conservative function, this part right here, that has to be our f sub x. And in a similar way, this part right here, that has to be our f sub y. So we have our partial derivatives. So what we have to do is reassemble this. And so what we're going to do is say, well, let's start with our partial derivatives and integrate. So we can say f, well, that's the antiderivative of f sub x with respect to x, right? It's a true statement. So let's take this antiderivative. So we're doing the integral, and I'm just going to copy this whole thing 2xy cubed plus 5y dx. So x is the variable. Treat any y's like constants. So in the first part, well, that's going to be x squared y cubed. All right, no worries. And in the second one, 5y, it's all constant. So 5xy plus our constant. Now, here's where it gets interesting. Because we're dealing with the multivariable functions, it's constant with respect to what you integrated. So anything that's a constant with respect to x, which includes anything with y's. So we're going to write this as some function which could involve y. Now, there might not be anything there. There might be. We don't know. Now we have to repeat it using the other piece of information. So again, I'm just going to copy that. So f is the integral f sub y dy. All right, so that's our 3x squared y squared plus 5x minus 2y dy, which is, okay, start here. Y is our variable. Treat x as like constant. 3y squared, take the antiderivative, that's going to give us y cubed. So we get x squared y cubed. 5x, all constant, so 5xy. Minus 2y, minus y squared, plus anything which doesn't depend on y. So a constant function just of x. All right, now, here's the next part. We're going to check for consistency. So consistency says, hey, let's make sure anything where they're overlapping, we're getting the same thing. So overlap says both variables are involved. So here I see an x squared y cubed. Well, I see an x squared y cubed, so that's good. These match. Here I see a 5xy. That's an overlap because this also has a 5xy. Those match. Good. And as long as anything with the overlapping matches, we're good. And so we're good. We know we're conservative. Well, we knew we were conservative before we started. Now, anything that's not involved in the overlap will also show up. So here's how we assemble our final potential function. So I say, all right, our potential function consists of the pieces which overlap. So we're going to get an x squared y cubed, and we're going to get a 5xy. Then, in addition to that, we're also going to get the pieces where we don't overlap. So, for instance, you have this y squared here, and what will that look like? Well, that's going to come down and be part of the function, minus y squared. There's nothing up here, so we don't include it. So, is that it? Well, this is a potential function, and we just need one potential function. And you might say, well, what's another one? Add any number you like. What number are we going to add? 0, because we just need one, right? We don't need to add an exotic number like 2. No, just 0 is fine. On a side note, you might say, hey, where was this y squared up here? Well, it was hiding in the d of y. That's why we have to do both. And there may have been parts that involved x, and if there were, they would have been hiding in the e of x. So you can't get f from just one piece. You have to get them from all of the pieces. All right, so good. We now have our potential function, and the end is in sight. We just need to plug in, and then we'll be good to go. So the integral along our any smooth curve, 2xy cubed plus 5y dx plus 3x squared y squared plus 5x minus 2y dy is this potential function, x squared y cubed plus 5xy minus y squared. Evaluate from starting at 2, 1, going to 3, 4. All right, so here's where it's going to get interesting. X squared y cubed, that's going to take a moment. So x squared, well, that's 9. Y cubed is 4 times 4 is 16 times 4 makes 64. We'll play with that in a minute. Then we have 5 times 3 times 4. We'll work on that in a second. 4 squared. Oh, that one we can do. Minus 16. Okay. Subtract 2 squared times 1. Okay, so that's a 4. 5 times 2 times 1. That's a 10. And then 1 squared is a 1. All right, now 9 times 64, that might sound scary, but if you think about it as 9 times 60, it's 540. 9 times 4 is 36. Put those together, you get 576. 5 times 3 is 15, times 4 is 60, so plus 60. And then we're going to subtract 16, and then we're going to subtract 4 plus 10 minus 1 is 13. So 576 plus 60, that would make 536. Sorry, 636. Got to roll over. 16 and 13 makes 29. So 636 subtract 29, giving us a grand total of 607. Whew! Okay, we made it. We made it. Now, let's do a quick recap. We knew once they told us any curve would work that we weren't going to do a line integral by doing it, like, oh, let's plug in this for x, let's plug this for y. No. We were all about finding that potential. It's like, we're trying to find our own potential by taking this course. And this problem says, well, find my potential. And so how do you find it? You have the partial derivatives, integrate, and check for consistency, put it all together. So you have the overlap, and then the non-overlap pieces, and there's your potential. Then you evaluate that, end minus start, and plug it in. And that's it. There we go. Woohoo! Nice! Evaluate the integral. Integral from 111 to 333, 6x to the 5th y squared z cubed dx plus 4 minus 2x to 6 y cubed z cubed dy minus 3x to 6 y squared z to the 4th dz. Oh, that's right, I'm in my z mode. Now, what does this mean? Well, what we're doing is it's a multivariable integral, and you'll notice we have here points. So it's saying, oh, go from the point 111 to the point 333. It doesn't tell us how we're going between those points. And so it's like, well, how do we go? Well, because it doesn't tell us, that says we can go anyway. Well, what does that mean? Curve independence means conservative, which means it's the nice kind, right? Yeah, so we're like, woohoo, this is the nice kind of integral. So we know our goal, our plan is we need to find our potential. So since there's no curve given, it must be that this is a conservative function, and so we have to find our potential. So we're going to run through the same process like the last problem, right? We say, okay, we have here, this is our f sub x, here's our f sub y, here's our f sub z. And now go through and put them together to figure out what does f look like. All right, so let's start. We have f, we're going to integrate f sub x dx. So that's the integral of 6x to the 5th y squared z cubed dx. The y squared and z cubed are constants. Integral 6x to the 5th, that would be x to the 6 over y squared z cubed, and then plus any function, we don't know which function, which is constant with respect to x. So anything which depends on y and z. All right, we also know f is the integral with respect to y, dy, so that's the integral of 4 minus 2x to the 6 over y cubed z cubed dy. Well, the integral of 4y. Now, here, the x and the x and z are constant. This is really like y to the minus 3. So what would you do? You'd add 1 to that power, so it would become y to the minus 2, divide by minus 2, so you end up with a plus, and the 2's cancel, x to the 6, and downstairs, y to the minus 2 comes a y squared z cubed plus, okay, some constant function which only depends on whoops, x and z. All right, now we also have f is the integral f sub z dz. Okay, that's the integral minus 3x to the 6 over y squared z to the 4th dz, right? Just the end part. See, we even group with the dx's, right? Put with the dx, put with the dy, put with the dz. Now, x and y's are constants. This is like z to the minus 4. Add 1, z to the minus 3, divide by minus 3. We have a minus 3 in front, almost like it had been planned. So the x stays as is, the y stays as it is, and then it'll become z to the minus 3, or z cubed, plus anything which doesn't depend on z. Now, time for us to do our consistency check. We say, is there anything which has multiple variables? If there are, they need to agree. Well, this has x, y, and z, so we have to make sure it shows up in every place. That agrees with that, and that agrees with that. So they agree. Consistency, that's a consistency check. So that's a verification that says, hey, this is actually a potential function. So our potential function will involve x to the 6 over y squared z cubed. Now we also check for any other parts. So these are pieces where they don't necessarily have multiple variables involved. Now it can, by the way, only have 2 variables involved and not just 3. Or it can just have 1. So that's this 4y. And so if we add 4y. So here's our potential. All right, great. So we found our potential. Are we done? No, because we're looking for a number. It's an integral. We want a number out. But this is the hard part. So what's the rest of it? Well, it's evaluating. And so we have that this is equal to, and we write down our potential function, x to 6 over y squared z cubed plus 4y, and evaluate from 1, 1, 1 to 3, 3, 3. So we need to plug this in. That is equal to 3 to the power 6 over 3 squared 3 cubed plus 4 times 3, subtract 1 over 1 times 1 plus 4. All right. Now, this looks like it might be complicated. You're like, what's 3 to the 6? 729? Yeah, but we don't need to know that. So just count your 3's. You have 6 upstairs, you have 5 downstairs. So altogether, this is a single 3. So it's 3 plus 12, which makes 15. Now here, you have 1 plus 4, which is 5. So 15 minus 5, which is 10. And there we go. Nice! Again, by not giving us information about how we got between the endpoints, they basically are trying to send us a signal, and we're going to pick up on their clues. They're telling us, hey, don't try to do this by some parameterization. Look for the potential, and then evaluate at the endpoints. That's what we did. Cool. Hey, it's me again. I just want to point out that you could actually do this a different way, which is to say, there is a pretty simple curve that goes from 1, 1, 1 up to 3, 3, 3. And namely, what's that curve? Well, it's the curve t, 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 where 1 less than or equal to t less than or equal to 3. And since it doesn't matter which curve we pick, let's pick that curve. Then what happens? Well, this integral becomes the integral from t equals 1 to t equals 3. Everywhere you see an x, put a t. Everywhere you see a y, put a t. Everywhere you see a z, put a t. If you see a dx, put a 1. If you see a dy, you put a 1. If you see a dz, put a 1. So we have 6 t to the 5th over t squared t cubed times 1 plus 4 minus 2t to the 6 over t to the 6, t to the 6 times 1 minus 3t to the 6 over t squared. Oops, I said t to the 6, that's t cubed, t squared, t to the 4th times 1 dt. Since it doesn't depend on the curve, pick a nice curve. Now, you'll see all your powers of t cancels, so you have 6 plus 4 minus 1, and then minus 3. And, whoop, forgot that 2. Okay, here we go. Let's be careful here. That's 1 to 3, 6 plus 4 minus 2 minus 3. And what is that? That's 10 minus 5. That's 5. So that becomes the integral from 1 to 3 of 5 dt. That's 5t from 1 to 3. 15 subtract 5, and that's 10. So this is a case where you could argue, hey, instead of finding a potential function, just find a nice curve. It's a perfectly valid way. If you did it that way, I just want to say, wonderful. That's awesome. Be open to both possibilities. The more ways you have to solve problems, the better chance you have of solving them. And the more you get comfortable saying, oh, you know, I could go down this route, but here's another way which might be easier. So, all right, anyways, back to our regularly scheduled programming. Evaluate the line integral along the curve x squared plus yz ds, where c is traced by this curve r of t parameterized by t, 5 minus 4t, 8t, and t goes from 0 to 1. Now, side note, we cannot be conservative here. This is not a conservative setting because there's no orientation given. This is a straightforward line integral, which means we're going to take our x, replace it by our x of t, our y is going to become our y of t, our z is going to become our z of t, and then our ds is going to become our square root of x prime squared plus y prime squared plus z prime squared dt. Okay? So that's what we're doing. All right, well, let's begin. Let's do our ds. That's oftentimes the most important thing to start because it's oftentimes the most work. Now, it looks like we have something that's not too unreasonable, but let's find out. Okay, so our ds is going to be the square root of our x prime squared, so that's 1 squared, our y prime squared, that's negative 4 squared, and our z prime squared, that's our 8 squared. Now that's 1 plus 16 plus 64, which, let's see, 64 plus 6, that's 81. Oh, 81. Nice, because that's 9 dt. Good. Good. Okay. Whew. All right. So that's going to make it a little bit easier because we're not going to have anything unpleasant underneath the square root. So here we go. The integral along our curve of our x squared plus yz ds is going to be integral. Use the bounds, 0 to 1. Now, x becomes t. So we're going to have t squared plus y becomes y of t. 5 minus 4t. Z becomes z of t. 8t. And then our ds becomes 9 dt. All right, and now we're almost there. Yeah, we just have Calc 1 type problem. We can pull the 9 out. So this is 9, integral 0 to 1, 9. Minus 4t times minus 8t. That would make minus 32t squared. And then 5 times 8t would make 40t. So let's put that 40t in the front. Then we have t squared minus 32t squared. That combines to give us minus 31t t squared. All right, and then dt. Okay, good, good. And it doesn't hurt to double check. So 5 times 8t, 40t, yes. T squared minus 32t squared minus 31t squared. Yep, that looks good. Okay, so we're really close now. So that's 9. And then we have 40t. Well, that's going to become t squared over 2. And so that's going to become 20t squared. And 31t squared will be what? Well, that's going to be 31 over 3 t cubed. Evaluated from 0 to 1. When you plug in t equals 0, you get 0. When you plug in 1, well, the powers of t become 1. So here you really have 9 times 20 minus 31 over 3. Well, you can distribute the 9 through. So 9 times 20, that's 180. And then here, the 3 goes into 9, right? So you really get 9 is 3 squared. So it's 31 times 3. So that makes 91. If you take 180 and, not 91, 93. I can multiply 31 times 3. I've done it before. Maybe. But at least I've done it once because I just did it. Okay, so where were we at? Oh, yes, we were talking about 180, subtract 93, and that would give us 87. And there we go. That's our answer. Woohoo! Nice! Evaluate the line integral along a curve C of 3x plus y times x plus 3y ds, where C is part of the circle x squared plus y squared equals 4, traversed, which means we just move, from 0 to 2, 0. All right, now, here we go. Okay, so what are we going to do? Well, let's draw our curve first. So we're going from 0 to, so 0, 2, that says you're up here, and 2, 0, and 2, 0 is over here. And good news, these are points on the circle radius 4, and so it's this part of the circle. All right. Now, what do we need? We need a parameterization. And okay, so here's a chance for us to have our talk, or one of our talks. When we're picking parameterizations, what's our goal? We want them to be nice because we are loving ourselves. We want to be kind to ourselves. So we always look for the nicest parameterizations. Now there's lots of parameterizations that we could pick. And so one parameterization that you might say is like, oh, what if we did the following? Because I can solve for y as a function of x. So this is y squared equals 4 minus x squared, or y equals the square root of 4 minus x squared. And then I can use this to say, hey, here's a parameterization. I can say C looks like the curve r of t, which is t comma square root of 4 minus t squared, where 0 less than or equal to t less than or equal to 2. Does that work? Absolutely. Will that be the cleanest one you could do? Probably not, but it will work. But I want to point out another thing that you can do. And I want to go in that direction, mostly because I just want to emphasize that when you see circles, circles have a natural built-in parameterization. And namely, if you think back to the unit circle, and as one often finds themselves doing, well, points on the unit circle are storing information about particular functions. And in particular, they store information about cosine and sine. So, say, okay, if you have a circle, you can almost always parameterize in terms of cosine and sine. You just have to be a little bit careful. Your little bit careful here is just saying, pay attention to your time and your orientation. All right. So, what do we do? Well, let's think about our first guess, right? You should always make guesses, and then does it work? And if not, refine and say, okay, Well, cosine t sine t is if we're a unit circle, radius 1. What do we have here? Radius 2. So you say, okay, how do you make it to radius 2? Well, you basically scale by 2. Okay, so guess 1. We could say 2 cosine t, 2 sine t. And that would be great. But there's one catch. Where does t go from? Well, if you said t equals 0, that would start here, and it moves counterclockwise, not in the direction we want. Now I'm going to make a side comment. I know I feel like I'm going off on tangents, but this is a calculus class. It's the one where tangents are encouraged. We actually don't really care about the orientation here. Why not? This is an integral where orientation doesn't matter. And so when you have an integral where orientation doesn't matter, then you don't have to worry. It's like, oh, this curve goes the wrong way. I don't care. All I care about is I travel the curve, whether forward or backwards. Life's fine. Okay, so we could work with this, but technically speaking, it starts at 2, 0, ends at 0, 2. So it's like, man, it's sort of doing the mere opposite of what we want. And so then it's like, oh, let's swap the roles of x and y. What happens then? Well, what happens then is you say it's 2 sine t, 2 cosine t. So at time equals 0, you're here. And then as you let time go to pi halves, you end up there. So our alternative is 2 sine t, 2 cosine t. And this is for 0 less than or equal to t less than or equal to pi halves. Either one gets you the same answer. Even this 2 cosine 2 sine 2 sine t gives you the same answer. So it's just a matter of pick your poison in some sense. All right, well, with this in place, we're basically ready to do the work. All right, now, why do I like this part? Well, because we have to do our ds. So reminder, ds square root x prime squared plus y prime squared dt. And I'm going to go with the circle, which uses sines, cosines. And why? Because that has really simple derivatives. So derivative of sine will be cosine. So it'll be 2 cosine t quantity squared. Derivative of cosine, negative sine, negative 2 sine t quantity squared. And all right, so that's 4. We both have 4 cosine squared plus sine squared. Like, cosine squared plus sine squared. Steve loves that. That's 1. I love it too now. It's 1, right? Because everybody loves this. It's like, if you're going to remember one thing from trig, it's like sine squared plus cosine squared equals 1. Like, yeah, you remembered the thing. Okay, so square root of 4, which is also known as 2. So ds is 2 dt. All right, well, here we go. And what do we have? Well, we have our integral along our curve. I'll write it back, 3x plus y, x plus 3y, ds becomes integral 0 to pi over 2 of, then we have our 3, and everywhere we see an x, we put 2 sine t, 3 times 2 sine t plus 2 cosine t, oops, not squared, times x, 2 sine t, plus 3 times 2 cosine t, and then ds is 2 dt. All right, well, we have a lot of 2's in here. In fact, let's go ahead and take the 2's out. I can have a factor of 2 I can pull out of here. I have a factor of 2 I can pull out of here. and have a factor of 2. So 2, 2, 2, 2, that's lots of ballerinas dancing around, lots of tutus. So that's 2 cubed, 2 8. So there's 2, 2, 2. And now we have 3 sine t plus cosine t, and sine t plus 3 cosine t dt. So let's expand. All right, so this will be 8 integral 0 to pi over 2, 3 sine squared t, and then we get 3 sine t cosine t times, well, 9, I should say, 9 sine t cosine t and sine t cosine t. So 9 here plus 1 here makes plus 10 sine t cosine t plus 3 cosine squared t. Okay, now our big aha. 3 sine squared plus 3 cosine squared gives us 3, right? Yes, yes. So that's 3. Now 10 sine t cosine t, this is the same as 5 times 2 sine t cosine t. And then we say, well, hey, sine t cosine t times 2, that's double angle formula. So this is the same as 5 sine 2t. Okay, so we now have 8 integral 0 to pi over 2 of 3 plus 5 sine 2t. All right, this is feeling more and more manageable every step we take. All right, well, let's try it out. Now, what do we get? So we have our 8 in front, and then we're going to have 3t integral of sine, negative cosine. So we're going to have minus, but divide by 2 to account for the 2 on the inside, 5 halves cosine 2t, and then we're evaluating from 0 to pi halves. Now, when we plug in pi halves, what do we get? Well, we're going to get 8 times 3 times pi halves, that's 3 pi halves, minus 5 halves times cosine pi. Cosine pi, though, is what? It's negative 1, so it becomes a plus pi halves, plus 5 halves. All right, subtract, plug in 0, you get 0, and then cosine 0 is 1. So there's a minus 5 halves there. So notice that really this becomes 5 halves plus 5 halves, which is 5. And then now the 8, distribute it in. 8 times 3 pi over 2, well, that would give us 12 pi. And then 8 times 5, 40. 12 pi plus 40. Done, done, right? And yeah, sure. I mean, it's a lot of work, but it's not too bad. It can be more challenging, but that's all right. We got through it. We made it to the end. Keep working these problems. The more you do, the more natural everything becomes, and that makes life wonderful. Because you're wonderful. You deserve wonderful things. Thanks for joining me. Let's see you again. Bye. You're still here? Well, if you're still here, let's do the other curve. And let's see, do we actually get the same answer, or was Steve bluffing? All right, well, that's fun. Let's figure this out. Okay, so let's start with our ds. So ds is our square root of our x prime squared. So here's our x prime. That'd be 1, right, squared. And then y prime squared. Okay, so that one maybe we can't do in our heads, but that's okay. So this would be, what would it be? It would be plus, it would be 4 1/2, 4 minus t squared to the minus 1/2, and then times by derivative inside, which is negative 2t, all that being squared dt. All right, now this will become square root of 1. The 2's cancel, that's good. The negative doesn't matter, And so what we really have is we have a t on the top, so that's a t squared. And then on the bottom, we'll have 4 minus t squared to the 1/2 squared, which makes 4 minus t squared. Oh, okay, well, I gave myself too much space there. All right, well, common denominator is 4 minus t squared over 4 minus t squared. 4 minus t squared plus t squared divided by 4 minus t squared would give us square root of 4 is 2 over square root 4 minus t squared dt. Okay, so that's our ds. Okay, we're doing good. Now, let's do our integral. So we have our integral along our curve, and before we plug in this expression, let's go ahead and multiply out, just so we know what's coming. So this is going to be the integral. We have 3x squared, and then we're going to get 9xy plus xy, so that's plus 10xy, and then plus 3y squared. All right, and that's going to be our ds. And okay, so this will become equal to the following. We're going 0 to 2, so 0 to 2, and x is t. So we have 3t squared plus 10. Now we have x is t, y square root of 4 minus t squared, and then plus 3, and again, y squared, so we're going to multiply this by 4 minus t squared. Right, the square roots and the squares undo each other, times all that by 2 over square root 4 minus t squared dt. All right, okay, good. Now, let's multiply all this through, and let's see what we have. Some things look like they'll be pleasant, and a lot of things look like maybe not so much. Okay, all right. Well, integral 0 to 2 of, we have 6t squared over square root 4 minus t squared. Okay, that's from the first term. Plus, the middle term, we'll have 20t, and then those terms cancel. All right, so that's fine. And then our last term, well, the square root of 4 minus t squared cancel, so it's plus 6 square root 4 minus t squared and dt. Now, two of these three are going to be quick. Namely, this one we're already happy with, and even this one we're happy with, not because we know it's antiderivative, but because if we say, oh, can we integrate 0 to 2 as square root of 4 minus t squared? Yes, that's part of a circle. It's very circulaceous. So it's like, okay, great. That part is going to be hunky-dory. Excuse my language. This one, we're going to work on it. Okay. So let's do the two parts that we can do. We'll do them right here. So the integral from 0 to 2 of 20t dt is 10t squared divided from 0 to 2, which gives us 40. All right. This part, we get 6 integral 0 to 2 of square root of 4 minus t squared dt, and we say, hey, really, if we think about what's going on, that's 1/4 of a circle of radius 2. And so we get 6 times 1/4 of the area of a circle of radius 2, which is pi r squared. Well, the 4 and the 2 squared cancel, and we're getting 6 pi. So we get 40 from there, and we have 6 pi from there. So what about this last piece? All right, we're going to need space. Okay, so let's work on that last piece. And at this point in time, you're probably thinking like, I'm glad we went with trig. Me too. All right, so how do you integrate something like 0 to 2 of 6t squared over square root of 4 minus t squared? We use trig substitution. T is 2 sine theta. dt is 2 cosine theta, d theta. And then we say, oh, well, this becomes, when t equals 0, sine of theta needs to be 0, so that's that angle of 0. For t equals 2, you need sine of theta to equal 1, which gives us pi halves. And what do we have? We have 6. And t squared makes 2 sine theta squared. And then dt is going to be a 2 cosine theta d theta. Now downstairs, when we work this out, well, we're going to have the square root of 4 minus 4 sine squared theta. Well, we can pull a 4 out, and then 1 minus sine squared is cosine squared, so it's 2 cosine theta. So 2 cosine theta. And those cancel. Almost as if it was meant to be, because it was. It was planned that way. From the very beginning, it was planned that way. All right. Well, great. So what's left? Well, we have this stuff upstairs. Okay. All right. Well, we got to do that too, don't we? And, well, what will we end up with here? 6 times 2 squared is 24. And so we have really integral 0 to pi halves of 24 sine squared theta. And now, how do you integrate sine squared? Half angle identities. So this is integral 0 to pi halves. 24 divided by 2, 1 minus cosine 2 theta. So that's sine squared theta is 1 minus cosine 2 theta over 2. And you say, ah, great. Well, that becomes integral 0 to pi halves. Oh, actually, we can just integrate. So that we have 12 theta minus integral cosine is sine. You need to put a half there to account for the half on the inside and evaluate from 0 to pi over 2. Now, the good news, when you plug in 0, sine of 0 is 0, and 0 is 0. When you plug in pi over 2, sine of pi is also 0. So what do you get? Well, you get 12 times pi over 2, which is 6 pi. So, coming back here, we've now worked that integral out. So our final answer is 40 plus 6 pi plus 6 pi. So you get 40 plus 6 pi plus 6 pi, which is 40 plus 12 pi. And now, moment of truth. The same answer. Coincidence? No, it's not at all a coincidence. It was meant to be. You'll get the same answer because it doesn't depend on the parameterization. However, when we compare the two processes, we say, this used some pretty straightforward trig identities. This used trig substitution. You're like, now I know what Steve means when he says we love ourselves. Always choose the best parameterization you can, aka simple. Simple things are wonderful. Just because something is simple doesn't mean it's incredibly useful. In fact, oftentimes the simpler things are the better things. So, all right, good. Now let's really go away this time, okay? I still love you. Great to see you, but we all need a break. So let's meet again next time.